So we are off to chapter 10 here, which is the second to last chapter of the season. We're going to talk about solutions here. So we're talking about some aspects of solutions. We're going to review some concentration units that we've talked about before, I believe. And then we'll get into some really the heart of sort of the chapter, which is colligative properties of solutions. So a couple of things that we've sort of talked about before, and sort of the idea of solubility. And when we talk about liquids in liquids, when we do have two liquids that really do mix together, there's oftentimes said to be basically soluble in each other. But sometimes when we're talking about liquids and liquids, the word miscible is used for those guys. And basically what that means is, obviously, if we mix two liquids, say in the same test tube, and they were soluble in each other, pretty much we would see basically sort of one layer, if you will, so everything would mix together. So an example of that is ethanol and water. And one of the major reasons why, say, something like ethanol and water can sort of interact well with one another is they really do use the same type of intermolecular forces. So they both are really using hydrogen bonding here. So ethanol is from my organic days, something like this. And ethanol, though, really has sort of this non-polar part. It has this polar part, this OH group, which is really the identical group that you have in water, as water obviously is nothing but OHs, basically. And water, which is polar, is more negative on the oxygen side, more positive on the hydrogen side. So this allows something like ethanol and water to really be soluble in each other because they will use hydrogen bonding. They can interact with this hydrogen bonding, and it makes them really sort of able to mix really well with one another. The nonpolar part of here in something like ethanol is small enough that it really doesn't get in the way of the interaction of the polar part. But what does happen is, if you were to sort of build out more carbons there, you get maybe 5, 6 carbons or more, the solubility really does start to drop a lot, almost to where it will be insoluble at that point. And what happens, though, at that point where you get, say, something like hexanol or heptanol, which is 6 or 7 carbons basically there on the back end, that nonpolar part gets so large that it really prevents sort of the water to get in there to the OH part of it, and it has a really hard time interacting with one another, sometimes referred to as steric hindrance. You have this kind of big end that sort of gets in the way. But usually something like ethanol, which is an alcohol, an organic alcohol that has like 5 or less carbons sort of attached, are fairly soluble because that nonpolar part hasn't got big enough to sort of prevent it. When two liquids really do not mix together, they're basically insoluble in each other, and they are also said to be immiscible in each other. And typically when we have liquids that really do not mix well, what we will see is layering of those liquids, say in a test tube, and they will basically layer out because they really will not mix together. So something like carbon tetrachloride, which is CCl4 in water, they have a really hard time working with each other. And that's because if we just quickly sketch carbon tetrachloride, it looks something like this without all the non-bonding electrons. And that is, we remember from our bonding days, there is a symmetrical geometry, which means this is a nonpolar molecule. And something like this, which is nonpolar, is definitely going to really have only dispersion forces sort of at its discretion to use in terms of intermolecular forces. While again here, water is going to want to do its hydrogen bonding. So for the long period of time, they really have no way to interact well with one another. Remember, dispersion forces are really weak forces that rely upon something happening to gain sort of a temporary charge to allow interaction to occur. So these guys definitely will not mix together. So the idea here is, and really what makes things sort of soluble in one another, is an idea that we sometimes talk about a lot when we talk about solubility, is the idea of like dissolves like. So things that use similar intermolecular forces as they use with themselves tend to be soluble in each other because pretty much they can do the same interaction with the other molecule as they can with themselves. So it makes them work really well with one another. When you start mixing things that really use two very distinctly different types of intermolecular forces, they have a very hard time sort of maintaining that interaction, and they basically usually will be insoluble in each other. So as we talked about a little bit before, probably if we were talking about things being soluble, if you have something that's ionic and polar, that's all good. If you have something that is polar and polar, that is okay. And if you have actually something that is nonpolar with something that is nonpolar, they both will use dispersion forces and they typically will be soluble in each other. It is really, again, we run into trouble in terms of insoluble or miscible when we do kind of cross over from something that is polar to something that is nonpolar. So those two guys are using, once again, very different types of intermolecular forces. Our polar molecules are going to be trying to use dipole-dipole interaction or hydrogen bonding, while again, our nonpolar pretty much has to stick with dispersion forces, which it's those temporary type of forces. Any questions on that there? This is also why when we talk about solutions and solvents, although water is a really good solvent for a lot of things that are ionic and polar, it's a crappy solvent for things that are nonpolar because they really will not mix. That's why if you're doing something that is nonpolar, you do need a nonpolar solvent to be used, like carbon tetrachloride or hexanol or hexane or something like that. That would maybe work. So again, we see some different layering when we get things that are immiscible, definitely some different layers that will happen because they really can't mix together. So things that are ionic are typically always soluble in water because they're able to do the ion dipole interaction. Really, that is what is happening there. And if you remember, that is pretty much an ion that gets surrounded by a polar molecule like water. And that's essentially what happens when a positive ion goes for a swim in water. The negative side of water, which is the oxygen, will surround it, while the negative ion will be surrounded by the positive side of water. And again, that helps it sort of dissolve. It helps keep the two ions away from each other because they have a very strong attractive force to one another. But there's such usually an incredible amount of water molecules when you dump water onto something that's ionic, that there's enough water molecules really to kind of pry those guys apart from one another and sort of keep them separated. There are things that are non-ionic. They're also soluble in water. So ethanol, as we just talked about, is also soluble in water. So is sugar. And really, they both have that sort of polar bond, that OH bond on them. And again, that gives it a very good opportunity to interact well with water. Something like sugar, which is a relatively larger sort of molecule, what sort of helps overcome that aspect of it is it's pretty much littered with OH groups all over it. So everywhere there's an OH group, it gives it an opportunity to interact well with water and makes obviously sugar very soluble in water because of that, even though it may be a little bit of a larger type of molecule. This is methanol, which is also an organic alcohol. And again, this part of it here is non-polar, where the carbons and hydrogens are. But once again, it has that OH group, which makes it able to hydrogen bond really, really well with water and makes it very soluble in water. There's our ethanol that we talked about a second ago. Now, when we take something like oil, it is typically insoluble in water, and that's because pretty much oil is nothing more than just an incredibly long chain of carbons attached to carbons, and attached to those carbons are hydrogens all the way across. I won't draw them on all of the carbons, but there's pretty much all carbons and hydrogens pretty much is what oil is. And the carbon hydrogen bonds we talked about with bonding, the difference in electronegativity is about 0.4, which is basically the limit for a nonpolar bond, which means pretty much oil is nonpolar. So oil wants to again use dispersion forces, while water obviously again wants to use hydrogen bonding. Now, everything, even polar molecules, does have the ability to do a little bit of dispersion forces. And that's why, temporarily you can get some interaction between, say, something like oil and water, or oil and vinegar salad dressing, and stuff like that. But over the long period of time, they have no way to maintain that. So if you just think about the salad dressing example, you can mix it up really well. But then once you put it down, eventually they will all kind of sort of separate out from each other. Also, why when we have oil spills in the ocean, right, eventually the oil just starts to float on the surface of the water, again, because they have no way to truly mix and interact and maintain that interaction over a long period of time. In addition, oil molecules are usually extremely sort of large molecules. So whenever we want to sort of dissolve something, say in water, we really have to replace what's there before. And before we do anything in terms of dissolving in water, we already have a bunch of water molecules basically attached to other water molecules. So to get something to dissolve, we basically have to replace water and water's interactions with very similar type of interactions. And water is not an extremely large molecule. So the second thing that really makes sort of oil not very soluble in water is the fact that it's usually a really large molecule. So it doesn't really fit really well with water either. It's kind of like, if you want to park your car in your garage, it fits okay. If you want to park like, a semi truck in your garage, you can get some of it in there, but it's not going to fit very well, probably in your garage and stuff like that. So that's the other part that really helps with solubility, is things that can interact really well with one another the same way they interact with themselves. And also, they're relatively the same sort of size as what you are trying to get it to dissolve in, also helps a lot. And again, it comes back to that idea of like dissolves like. Now, when we have interactions and some of these molecules that we talked about here, there are different sort of parts to these molecules. For example, ethanol is an example of a molecule that has really two different regions on it. It has a nonpolar region, which is basically those carbons and hydrogens, but it has this polar bond here at the end, which is sort of a polar region. So a molecule like this, has the ability to interact, well with water because of that polar region. Now, a region where we do have that polar region, because it's able to, for example, hydrogen bond with water, is sometimes referred to as being hydrophilic, which means it likes water. And there's also a part of the molecule that is sometimes referred to as hydrophobic, which means it does not like water. So that would be the nonpolar side. That's also how soap works. Soap is basically a long chain of carbons and hydrogens, and that's what my little line structure is. There's carbons at each of those points, and they also have hydrogens as well coming off of it. And at the end of, say, soap, there is a polar type group, which is known as sort of a carboxylic acid type group. And this group here, which is polar, is sometimes referred to as the polar head of soap. And this part, which is all carbons and hydrogens back here, which is nonpolar, is sometimes referred to as the nonpolar tail of soap. And really, this is what gives something like soap actually the ability to interact with both polar and non-polar molecules, because it does have these both regions. It has a hydrophobic region, which does not like water, but likes non-polar things like dirt. So most dirt is non-polar. So when you soap up, the non-polar side of soap basically is attracted to the dirt, and it basically traps all the dirt on the non-polar side of soap. When it does that, it sort of positions the polar side out from the inside where you have all the dirt trapped, and that polar side likes water, which is typically what we'd use after we use soap, right? Or in the process of using soap is we wash it with water. So when you wash it with water, the polar side of soap and the water mix really well. It has all the dirt trapped on the non-polar side. It creates what's known as a micelle, where a bunch of soap molecules basically, kind of surround the dirt and trap it. And then the polar side of soap basically is on the outside. So when you wash it with water, out goes the soap that has the dirt trapped on it, which is how we are clean. These are good things to know, I suppose. Any questions on that there? So here we have octane, which is basically 8 carbons in a row. And it is soluble in carbon tetrachloride because that also is nonpolar. So these guys are going to be using dispersion forces. And as you can see, we pretty much get one layer that happens. And that's different when we take gasoline, which is pretty much like octane. We get that layering that happens. And again, usually when you do get that layering of something that's nonpolar with something that is like water or water-based, usually the nonpolar guy is up on top and the water part's usually on the bottom. We saw that way back when we did that experiment with the halogens where we had the different layers. When we use heptane, which is nonpolar, it had the top layer, and on the bottom layer was the sort of water layer. Now, when one substance is again sort of soluble in another, and usually that's how we make a solution. We take the solute and we dissolve it in the solvent. It is said to be soluble. So any type of ionic compound will be soluble in water because it's able to interact well. When another substance does not dissolve in another, that is said to be insoluble. So oil is insoluble in water. There is a limit to the solubility of one substance in another, and it is sort of temperature based. So at a particular temperature, for example, you only get so much of a solid to dissolve. That's why sometimes they will tell you to heat up a solid if you're trying to get it to dissolve in water. It's not dissolving. When you heat it up, you actually increase the solubility of a solid in, say, water or something like that. You also, by heating it up, is supplying more energy, which allows everybody kind of start breaking apart and starting the dissolving process. Gases, though, are always soluble in one another, and that's just because gases are, frankly, flying around. So because gases are constantly flying around, they're constantly mixing with one another, which obviously means that they are soluble in each other. Some liquids are also mutually soluble, so that's our polar-polar, non-polar guys that are equally soluble in each other. At a higher temperature, which does play a role obviously in solubility, we typically have a larger solubility of a solid in a liquid. Again, increasing the temperature, as I just mentioned, does increase the energy, and it really does help everybody start moving around. Something that's an ionic solid is pretty much locked into place, but once you sort of increase the temperature, that's sort of how we start to transition from, say, solid to liquid. Everybody gains more energy, so they're starting to move, which will allow them to start to dissolve a little bit easier. At a lower temperature, we typically have a larger solubility of a gas in a liquid. And that is because at a lower temperature, as we know, our gas molecule is moving slower, which means if it's moving slower, it's going to be in the liquid part for a much longer period of time as it is flying around before it's able to exit, which means it will stay in that liquid part for a much longer period of time. Also, the solubility of gases does depend on pressure. The higher the pressure, the larger the solubility of a gas in a liquid, for example. Excuse me. When we have a higher pressure, what does that mean for the volume? For all of our Boyle's law needs, the volume goes down, right? So at a really high pressure, what we have is a much smaller volume for that gas, which means the gas molecules are definitely near each other for a much longer period of time, and they're constantly mixing because they're in a much smaller volume because of that. So we also could talk about solutions and sort of describe them in a couple of different ways. One way that we could describe a solution is what is known as a saturated solution. And a saturated solution is a solution that basically has the maximum amount of solute that will dissolve in that solvent at that temperature. A reminder that when we do talk about a solution, those are our guys with the aqueous symbol, and there are two parts to a solution. There is the solute, which is the smaller part, and there is the solvent, which is the larger part of the solution. So when you basically hit the saturation point, that is the part where we pretty much have got 100% of what we could dissolve at that temperature dissolved in the solution. If we continue to add more solid to try to dissolve it, it will not dissolve. It'll just sort of pile up there on the bottom of whatever it is, the beaker, the test tube at that point. The opposite of that is we really haven't hit that point yet. So that is what is referred to as an unsaturated solution. So an unsaturated solution is a solution where you basically can continue to get solid to dissolve, and it will continue to dissolve until you pretty much hit a saturated solution. So an unsaturated solution, you can keep dissolving the solid, it will dissolve until you hit that point when you hit a saturated solution. And obviously at that point, no more solid will dissolve. Another type of solution is one that's referred to as a supersaturated solution. And a supersaturated solution is usually made a couple ways, but one way is you take a solution that is a saturated solution and you kind of heat it up as you're making it. And when I start heating up this solution, what's going to happen is the solubility from room temperature to the hotter temperature that I'm heating is going to increase. So again, solubility, say, of a solid will increase with temperature. So as I'm sort of warming the solution up, that will allow me to get more and more of, say, the solid at this point to dissolve in the solution. And once you get the amount of solid that you want to dissolve in the solution, what you typically do as you're making the supersaturated solution is you pretty much let it cool down without kind of disturbing it, without touching it, without looking at it wrongly or anything like that. So what happens as this solution starts to cool back down, say, to room temperature, the solubility of that solution has now also come back down. The problem is you've already dissolved a bunch of solid in that solution. So what you have now is a supersaturated solution, which is essentially a solution that has way too much solute dissolved in it. It is like we're now back to room temperature, but you already kind of stuck all that solid in there. Kind of like when you shove a whole bunch of stuff into like a closet door and shut it really quick. Like, hey, it's in there, but it shouldn't be in there, right? Because you know, as soon as it's going to pop open or somebody opens it, it's all going to come out. And that's sort of what a supersaturated solution basically is. It's a really unstable solution at this point because the temperature has dropped back down, so the solubility has decreased, and now we have way too much solid dissolved in it. It is so unsaturated that, frankly, if you took just a speck, like that small of a speck of whatever you dissolved in it, and you dropped it into the solution, that one little speck, that solution would go, whoa, too much. And what will happen is all of the solid will start to come out of the solution. So it'll go from like a liquid phase to like a rock hard solid at that point. You basically will drive all of that solid out of the solution because it knows it is too much basically to be in there. This solution is also so unstable that, frankly, if you tap it by accident or put it down too hard on like the bench, that's actually enough to cause it all to come out of solution. I know this because I demonstrated like a week ago, and the accident just lifting the flask up is enough to sometimes cause basically the solid to come out of solution. So that's really how unstable a solution like this is, because you have, like, again, way too much of that solid dissolved in there. Any questions on that there? So this is that experiment. Actually, it's a very common one. They don't do it here, but some schools used to do it. Not too many anymore because it caused a lot of problems. But this is a supersaturated solution, and you can barely see it, but he's taken basically just a very small drop right about there. And that drop hit right about there. And you can start to see that is all the solid basically starting to come out of solution. And it looks just like that. It's like it's starting to kind of crack and come out. And again, it will end up as a very sort of hard, solid solution at that point as all the solid comes out. A lot of schools used to let students do it in a test tube, but they would have them put their thermometer in there. And then when they would disturb it, their thermometer is now a lollipop, right? Because it's stuck in their test tube. So students are always going, how do we get it out? Break it? No. So the right way is you would have to reheat it up, right? If I reheat that, it will once again be hot enough to allow that solid to redissolve into solution, and you can pull your thermometer out. So it shows the idea of solubility and temperature. Again, at a much lower temperature, you have a less solubility of a solid in a liquid. Higher temperature, you can get a lot more solid to sort of dissolve. Any questions on that there? Which is why also, if you remember when you did titrations, some of your solids were kind of difficult to dissolve, right? So some schools will tell you to just gently warm it to allow basically that guy to dissolve, and then you can go do your titration to get those guys to dissolve. Now, the relationship between pressure and gases, there's actually a relationship which is known as Henry's law. And Henry's law is basically the soda can example of this. And it basically says the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. Here's two versions of Henry's law. C is equal to K times P. C is concentration or molarity. Usually molarity. K is actually Henry's law's constant, and it is specific for different gases. So you would look it up in a table. You know, if you're talking about CO2, you would go find the Henry's law constant for CO2. If it was some other gas, obviously you would look it up for some other gas. P is the pressure in atmospheres. This is the other version of it. The only difference is the S stands for molar solubility, which is a fancy way of saying molarity as well. So molar solubility is what the little S stands for. The other part's the same, the K and the P. So here's a table of Henry's law constants. Like I said, you would look them up based on the actual gas that you're dealing with. So if we look at an example of this, and I think we might have talked about it when we were talking about gases, but this is the solubility under pressure. Before, again, you pop your soda can there, it's under a lot of pressure, which means the CO2 that's in there is more soluble in the liquid part of your soda, which is basically water, syrup, and whatever type of soda you got going on there. So you have a lot more of that CO2 dissolved in the liquid part. Obviously, as you pop the top, you are releasing the pressure, and you're also, as you can see here, giving the gas an escape route through the top of your hole there. That is also going to allow the gas molecules to escape the liquid part and also escape your can. That is why when you come back later, right, your soda is flat because all the CO2 bubbles, right, basically escaped as the air kind of pushed it away there. So if we were to do a calculation like this, what is the pressure of CO2 that's required to keep the concentration of CO2 at 0.12 molar at 25 degrees? So here is the KH there for CO2. So why don't you take a second and calculate that? Okay, so obviously here we'll use Henry's law, whichever version you like. C is equal to K times P. In this case, we do have the concentration of the CO2 given to us. Obviously, if this value was not given to us in the problem, you would go to a table and look up CO2 and find the constant, which is this. That means that the pressure here would be the concentration divided by Henry's law's constant. Our concentration would be 0.12 molar divided by 3.4 times 10 to the minus 2 molar over atmospheres. Molarity on the bottom and top will cancel, and we will end up with making sure to use a little exponent action there. About 3.5 atmospheres, which would be the units for our soda. So it's about 3.5 times, right? Normal pressure of 1 atmosphere, right? Is our soda, how is it popped in there? Any question on that there? Hopefully they agree. That's good. All right. Now, we talked about a number of these concentration units, but just to review some of these guys that we went through, there's some percent concentrations that we talked about. We talked about percent by mass, which is percent mass to mass, which is the mass of the solute over the mass of the solution times 100%. Remember, in this case, this one is really important, as you want to make sure that you do get the solute and the solvent as we did before. Remember that it is very often sort of separated out. Some other percent concentrations we talked about, percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. We also talked about percent mass to volume, which is kind of like density, the mass of the solute over the volume of solution times 100%. So remember that these are three sort of concentration units. If you're given the percentage, you can also turn them into conversion factors, like I think we talked about when we were doing all the molarity and all that in those chapters. So again, if we had a 4.5% by mass sodium chloride solution, that would mean that there are 4.5 grams of sodium chloride in 100 grams of solution. Or again, if you needed it sort of the opposite way, you could flip it around and do 100 grams of solution would have 4.50 grams of sodium chloride. So again, you can do a more dimensional analysis approach and to solve some of these problems using the percentage. You could also do it for any of these other ones as well. This is typically milliliters over milliliters, and this is typically grams over milliliters in terms of the units that we typically use for those guys. All right, so again, I believe we did this example earlier on, but we are making 2.5 grams of calcium chloride with 50 grams of water. Remember that we would want to, in this case, add both of those numbers together to get our mass of the solution, which in this case should be 52.5 grams. And that is what we want to use on the bottom of our calculation, where we would take 2.5 grams divided by 52.5 grams times 100%. And that gave us our percent by mass of, I believe, 4.76% by mass calcium chloride. Any questions on that one there? Again, as we talked about, I think when we went over it the first time, it is a very common mistake. People just use the solvent part of it, again, not the entire solution part. All right. Molality. Not sure if we talked about molality or not, but let's talk about molality here. Molality is different than molarity. And molality is actually little m, and it is moles of solute divided by kilograms of solvent. So that is different than molarity, which is obviously our moles of solute divided by liters of solution. So you shouldn't get these two confused. Obviously, the moles of solute is sort of calculated the same way. You basically could take grams to moles, but again, on the bottom, it's just kilograms of solvent. So if you had a 4.5 molal sodium chloride solution, that would mean you had 4.5 moles of sodium chloride in a kilogram of solvent. So just like molarity, the number stays with the moles part and is per 1 kilogram on the bottom there. The sort of one that ties both of these together, or if you do need to kind of go between these two, it's oftentimes density that allows you to kind of go between the two if you had to kind of go back or forth. between molarity and molality. So if you do see the little m in context of solutions, it is molality, it's not mass, and again, it's not molarity, and they are two different things. So if we wanted to calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH and 175 milliliters of water. So once you take a moment and calculate it, carbon is 12.01, hydrogen 1.008, and our oxygen still 16 here. All right, so calculate the molality here and see what you come up with. Okay, so we're looking for the molality here, and once again, the molality is our moles per kilogram of solvent. In this case, the water is our solvent, and this guy here would be our solute. So what we need to do obviously is convert that guy into moles. So we have 3 times 12.01 for the carbon, plus really 8 times 1.008 for the hydrogens, and we got 1 oxygen there. That's going to give us, I think, 6009, if I'm not mistaken. That gives us 6009 grams per mole, which would be the molar mass of our C3H7OH. We'll use that obviously to convert our grams into moles. We're going to divide by it. And we will end up with 61.7 divided by 6009. Going to get a 1.03, we'll round it to moles of our solute in this case. That would be the top part here. Now for our solvent, we are given the volume, but we do need really the kilograms. So they gave us the density of water. So we can take our 175 milliliters of water. We can use the density of water, which would be 1 gram per milliliter. The milliliters cancel, means that we have 175 grams of water, which is close to what we need, but we do need kilograms. So I believe there are 1,000 grams in a kilogram, if I'm not mistaken. That will give us 0.175 kilograms of our solvent. At this point, we have everything we need to calculate the molality. So our molality here would be 1.03 moles over 0.175 kilograms. And that gets us 5.87. And you can leave it as moles per kilogram, or you can write 5.87 little m in that particular case. So I think we went over this before, but just a reminder, since this is actually really important for colligative properties, we use molality a lot in those sort of formulas. Any questions on that one there? So molality, again, as we're going to talk about colligative properties here, is used a lot. We obviously have talked about our mole fraction, which again is the moles of what you're interested in divided by the total moles that are there. It's really kind of like a percentage without multiplying by 100, so it's kind of a point something type number. So again, our mole fraction, moles of A divided by, say, the total moles. So we take a look at that. So in this case, I think that we did this example earlier on in a previous chapter. Calculate the mole fraction of methyl alcohol that's composed in a mixture of these 3 guys, or 2 guys. We would add them together, the total moles on the bottom, the moles of what we're interested in, and we get 0.261. A reminder that if we wanted the mole fraction of the other component here, since there's only 2, we could just actually take 1 minus that number, and that would get us the other one. It's like taking 100 minus it, but since it's not a percentage, we use 1. Clearly, hopefully you haven't forgotten about molarity as well. Again, molarity is the most common unit of solution, which is moles per liter. And as we've talked about a number of times throughout our chapters here, we do rearrange this a lot and solve for any one of these three things. Remember that you do want to use liters for the volume when you're using molarity by itself. The one place where it's okay, again, is if you're doing sort of the dilution equation, you can use milliliters. But a reminder that if you take milliliters times molarity, you do get what are known as millimoles and not moles. So there is a difference than taking liters times molarity, which gives you actually moles. Probably 99 times out of 100, that is your end destination there, which is moles and not millimoles. So that's why we, again, want to make sure that we do convert it to liters when we are using molarity. All right, so with that being said, we're going to talk about some colligative properties of solutions. So colligative properties really of solutions are based on really the number of particles that are dissolved in the solution. So really the more particles that are dissolved in the solution, the greater impact it's going to have on sort of normal things. So for example, what does that mean? If we were going to take, say, water by itself, and we wanted to boil water. If it was just water, what would happen obviously is as we start to boil, we maybe overcome some of these hydrogen bonding. We'll get some water vapor that is strong enough to make these bubbles basically, and basically make their way out and start to boil. Now, if we take something and basically add something to water, so that is not pure water at this point, what we have now when we go to, say, a process like this is a couple of things. We have like our water molecules that are, trying to boil. We also have other things that are dissolved in there. I'll just make X's like we're playing football here. So we have the defensive line there, and those are our offensive here. And now what happens is we got all these particles basically kind of in the way. And what happens is it kind of gets in the way of the natural process that water wants to do, like we have on the left here of, it kind of has almost like a free run to get to the surface. It's now going to kind of work its way out, fake back this way, cut across that way, go deep for the touchdown right there. But now it's got a lot of these different particles that are in the way. And what it ends up happening is it actually creates a lot more energy that's necessary for those water molecules basically to escape and actually go and start to boil. The result of that is we see that the boiling point temperature of the solution will actually start to increase. So instead of maybe boiling like pure water would boil at 100 degrees Celsius, it will now boil maybe at 101 degrees or 102 degrees Celsius. So we'll see actually an elevation in the boiling point because, again, it takes a little bit more energy to kind of get through all the particles that are basically in that solution. Same idea if we're talking about, say, the natural process of, say, water molecules kind of coming together and starting to freeze, right? So in, say, pure water, we have sort of an open and easy way for those water molecules basically to kind of lose energy and start the hydrogen bond with one another and kind of go into sort of the freezing stage. Once again, if we kind of dissolve some stuff, in with the water molecules, we got, again, things that are going to sort of get in the way of the natural process of those solvent molecules coming together. The result of that, as we will see, is actually the freezing point will be depressed. It actually will freeze at a lower temperature as everybody's trying to work their way around to actually get themselves into that solid phase. That is why, like rock salt, right? And you want to make some ice cream, right? So you put some rock salt and some ice, right? It gets really, really cold. Homemade ice cream, YouTube it, I don't know. But, it lowers the freezing point. Also, as we'll talk about, is where we put like antifreeze in our car, right? We put antifreeze in our car. It actually does both things. It elevates the boiling point of the water in your car. So if you live in a really hot environment, it means your water in your car will have to get to a much higher temperature to boil than it would if it wasn't there. and also why if you live in a really cold environment, it lowers the freezing point, so everything in your engine doesn't freeze because it takes a much lower core temperature for that to happen. So antifreeze actually does both things. It actually elevates the boiling point and lowers the freezing point of the water in your car. So one colligative property that's affected by the particles that are dissolved in there is the vapor pressure, and it actually will lower the vapor pressure, hence the name vapor pressure lowering. A reminder that the vapor pressure, right, is at the surface of any liquid. We do have that process of guys sort of jumping out of solution and really guys kind of coming back the other way as well. And the vapor pressure is the number of gas molecules that are above a liquid phase. The greater number of gas molecules above the liquid phase, the higher the vapor pressure. Things with very weak intermolecular forces, as we talked about, have a very high vapor pressure because it doesn't take a lot of convincing for them to basically go into the gas phase. So they're able to sort of escape above the liquid. So the vapor pressure of a substance depends really on the nature of the substance and the temperature. If we add a solute, a non-ionic solute, and what non-ionic means is basically it will dissolve, but it will just go for a swim. No ions are being produced or anything like that. So, you know, you kind of like a non-electrolyte, you kind of dump it in there, it will dissolve, but it will not break apart into ions. We can do this by PZ, which is the vapor pressure of the component in the solution. XZ is our mole fraction of that component, and the P naught here is the vapor pressure of the pure substance. So say the substance without anything dissolved in it. So this is the vapor pressure of the solution that has stuff dissolved in it. This is the pure sort of solution without stuff in it, our solvent, and that is our mole fraction. So the vapor pressure lowering may be defined as the vapor pressure of pure substance minus the vapor pressure of the solution. And that's because the vapor pressure of the solution will be less, hence the lowering part. So the change in the pressure, you take the higher minus the smaller, and you'll get the change in the actual pressure that will happen. So let's take a look at this here. The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution that is made by taking 0.2 moles of glucose that's dissolved in 1.25 moles of the alcohol. So take a moment or two and see what you come up with here. Okay, so we're going to use our equation, which is the vapor pressure of our solution that has stuff dissolved in it, times the mole fraction, times really the sort of guy by itself with nothing dissolved in it. So that would be our 66.5 torr. That's our vapor pressure, really pure ethyl alcohol. We're looking for ethyl alcohol here. So that is the mole fraction that we want to calculate. So our mole fraction of the ethyl alcohol or ethanol would be 1.25 moles divided by, again, our total moles in this case, 0.2 plus 1.25. I think gives you a 1.45. And that's going to give us something, 1.25 divided by 1.45. Will give us about 0.8621, about 86%. And that would be our mole fraction. So our vapor pressure here would be 0.8621 times 66.5 torr. And that would get us 66.5, about 57.3 torr. This is vapor pressure lowering, and that's what we see without any glucose, which is basically a non-ionic solute dissolved in there. The vapor pressure above the ethyl alcohol is 66.5, which means they're able to kind of escape and get into the gas phase with a lot less problem than when we start to put extra particles there that get in the way. So again, they're going to sort of get in the way of the molecules being able to escape to the surface. So less of it's going to escape to the surface in this case. And what the result of that is, we have less gas molecules over the liquid, and we see that the pressure comes down from that, which again is the lowering part of it. And obviously the change in pressure would be 66.5 minus 57.3. It drops by about 9.2 torr in terms of the pressure by dissolving 0.2 moles of glucose in there. Any questions on that there? Yeah. This particular one does not have to be in atmospheres. The one that we saw earlier with Henry's law, that one does need to be in atmosphere. And it's really because in that equation, the Henry's law constant is usually in atmospheres. That way you got the right units, so everything cancels out. But in this case, since we're not using a constant like that, you don't have to worry about the units. Other questions? Okay. All right, that's what we just did. Good. Now, another aspect of colligative property, as I mentioned, kind of with the antifreeze, is the idea of freezing point depression. So again, the addition of these added solute particles in that solution is really going to get in the way of the natural sort of the molecules come together as they come into the solid phase and start to freeze. So there is a formula here, which is the change in freezing point temperature is equal to Kf times M. So this first guy here on the left is not the temperature at where it freezes. It is actually just the change in freezing point temperature. Did it go down 2 degrees, 3 degrees, 4 degrees? So that is the change in freezing point temperature. Kf is the freezing point constant. And that is typically a table value that you would look up. And most people have a really difficult time when they go to that table because they are looking for the wrong thing. So when you go to that table for a freezing point constant, it is based on the solvent, not the solution. So for example, somebody has like a sodium chloride solution, they'll go to the table and go, I can't find sodium chloride anywhere on this table. The sodium chloride example, the solvent would be water is what you would want to look up. So a lot of times it is water that you would be looking up and sort of using in these calculations. But remember that water would not always be the solvent. So you want to make sure that when you go to that table, it is the solvent that you're looking up and trying to find. The little m here is our molality, which again is our moles of solute over kilograms of solvent. So that is what we were just talking about. Now, because this is a freezing point depression, that means that the solution that has stuff dissolved in it will actually freeze at a lower temperature than the actual, say, solvent by itself. So say pure water by itself, again, would freeze at 0 degrees Celsius. If you add some stuff to it, maybe the solution that you made, like throwing some rock salt or sodium chloride or some other solute in there, maybe it'll freeze at minus 5 degrees Celsius or something of that nature. So because the actual freezing point goes lower, the change in the freezing point temperature is defined as the temperature of the solvent, which is actually the larger number, minus the temperature of the solution that will freeze at a lower temperature. This is really important when you're doing these problems because a lot of times you're not necessarily asked just what is the change in the freezing point temperature, but you're asked what is the actual freezing point of the solution. So if you remember that in this case, it is the solvent minus the solution, that will allow you to add when you should be adding and subtract when you should be subtracting when you go to solve for this guy, which is very commonly what you are asked to solve for. So kind of always the larger guy minus the smaller guy usually will get you the right adjustment that you need there. Now for boiling point, again, as we also talked about, it works really the same way. And It has a very similar sort of formula as well. The change in the boiling point temperature will equal Kb times the molality. So once again, this guy is our change in boiling point temperature. And by the way, these guys are actually typically left in degrees Celsius because the Kb and Kf values are also in degrees Celsius. So this is one of the few things that you don't actually have to convert to Kelvin in most cases because of the constant. Once again, this is the boiling point constant. And just like with the Kf, that also is based on the solvent is what you want to look for. And our molality, which is our moles per kilogram of solvent. Once again here, in this case, what's going to happen is because they're trying to escape the solution, it's actually going to take a little bit more energy to get them to do that, to get it to boil. And we will see again the actual boiling point actually elevate. So in this example with boiling point, the water will boil, say, at 100 degrees if it's pure water. By adding the solute to it, it's going to cause basically that solution to boil above 100 degrees. So that's the elevation part of it. And that also affects sort of the definition of the change in boiling point. That is the temperature of the solution, which actually will be a higher temperature minus the temperature of the pure solvent, which will be a lower temperature. So in this case, it's opposite of freezing. It is the solution minus the solvent, as opposed to the opposite in the previous one, the solvent minus the solution. And again, it's important to remember this, as it will allow you to do the proper either addition or subtraction depending on what you're solving for. Again, in a lot of cases, you will be solving for that value right there at the very end. Any questions on this? These are the two formulas that we use for non-ionic solutes. And again, these are non-ionic solutes, which basically means they will dissolve, will create no ions in solution. When we do have ionic solutes, which we'll talk about at the end here, we do have to do some adjustments to these formulas here to account for the increase in the number of particles. Here is a table of both the Kf and the Kb values. And as you can see here, it's a list of different solvents. And the important thing, obviously, is a couple of things. Although a lot of stuff that we will deal with will be water, which, as we know, right, the freezing point is 0 degrees Celsius, right? And the boiling point is 100 degrees Celsius for water. If your solvent is not water, you also need to adjust the freezing point and boiling point for that particular solvent. For example, benzene, freezing point is 5.5 and boiling point there is about 80. So you want to make sure that, again, if it is not water, that you use sort of the correct values for the temperatures of the freezing point and boiling point. For us, we will use, again, 0 and 1.86 as our Kf value a lot in problems. And the units here are degrees Celsius per molality, which is why we can leave the temperature in Celsius, so everything cancels out okay. And for the boiling point part, 0.512 degrees Celsius per molality for the Kb. But once again, if you went to this table, you would want to look up the solvent. All right, so why don't we try one here? What is the freezing point of a 1.7 molal aqueous ethylene glycol solution, C2H6O2? The Kf there is for water 1.86. Let's see what you come up with here. Okay, so let's take a look. So obviously we're dealing with freezing point, which means we want our change of freezing point is our Kf times our molality. If I were to go to the table, because maybe this wasn't given to me, the aqueous part means water environment. So that is, again, how I would probably know that I should be looking up water here as the solvent in the Kf value. In this case, we did not have to calculate the molality since they did it for us, but you may have to calculate the molality yourself in some problems. So really, we have everything that we need to stick into here. That would be 1.7 molality times our Kf value from the table. The molality will cancel, and that will give us 1.7 times 1.86. That's about a 3.2 degrees Celsius. Now, it's important to remember that this number right here is not the freezing point of this solution. It is actually the change in freezing point temperature. So this is where we want to use our change in freezing point temperature. In this case, it is freezing point depression, which means it is the temperature of the solvent where it normally freezes minus the temperature of the solution. So the change in freezing point temperature is what we just solved for, 3.2 degrees Celsius. Our solvent, which is water, means that it has a normal freezing point of 0 degrees Celsius minus the temperature of the solution. I'm going to bring this to the other side and bring that back to the other side. And what that's going to give me is a temperature of the solution is equal to 0 degrees Celsius minus 3.2 degrees Celsius, which means minus 3.2 degrees Celsius is the correct freezing point for this guy. Not 3.2, because if it was 3.2, it actually would have froze at a higher temperature than water, right? So this is what the importance of those couple equations are to make sure that you could get the correct sort of answer without giving just the change in freezing point temperature. You do want to be careful on these problems because sometimes they do ask for what the change in the freezing point or boiling point temperature is. And in a lot of cases, though, they do ask for what is the actual temperature at which they freeze or boil. Any questions on that one there? All right, so again, the addition of the ethylene glycol lowers the freezing point of our water from 0 degrees to minus 3.2 degrees Celsius. There we go. All right, so I want to try this one. We want to calculate the molar mass of a compound. By the way, molar mass is grams per mole, right? Of a solution, if 12 grams of it dissolved in 80 grams of water and it freezes at minus 1.9 degrees Celsius. Give it a go, see what you come up with here. Mass here. And again, the units of molar mass there are grams per mole. So we want to take a do we have any of that information given to us? We want to calculate the molar mass of a compound if a solution of 12.0 grams is dissolved in 80 grams of water. So that is the solute, and that would be our solvent. So usually the molar mass would go with our solute. So we do have the grams part. But really the thing that we're missing is the moles part here to allow us to really calculate the molar mass. And we could get that really from the freezing point information. So we could use our freezing point equation, which is Kf times the molality. And we obviously, since we know water is our solvent, we can find our Kf value. And we can find a change in freezing point temperature as well. So that's good. So that would mean that we could actually solve for molality. And that would be good because molality would be moles of the solute over kilograms of the solvent. And that would allow us to perhaps get to the moles of the solute, which is ultimately kind of what we need to finish out the calculation. So there is an important note here, which is the number that they gave us, which is this solution freezes at minus 1.94 degrees Celsius. That is actually the freezing point of the solution. That is not the change in freezing point temperature. So we do need to use our change in freezing point sort of idea where the temperature of the solvent minus the temperature of the solution. And our change in freezing point would be 0 degrees Celsius for our solvent minus the temperature of the solution, which is minus 1.94 degrees Celsius. That is actually how we get rid of the negative that we don't want. It is actually the change in freezing point temperature is it went down by 1.94 degrees. And that is, again, how we try to turn it into a positive number. Now that we have that, the molality here would equal the change in freezing point temperature divided by the Kf. That would give us 1.94 degrees Celsius divided by our 1.86 degrees Celsius divided by molality. The degrees Celsius will cancel. When you divide it, the molality will flip to the top, and that will get you 1.94 divided by 1.86 will get you 1.04 molality, which is basically 1.04 moles per kilogram of solvent. Any questions on that so far? Now, my solvent was the water, and they told us how much water we used, which was 80 grams. So we could take our 80 grams of water and convert it into kilograms, which is 1,000 grams is a kilogram, 0.08 kilograms. So if we multiply that by our molality of 0.0800 kilograms, kilograms of solvent will cancel, and we will end up with 0.0834 moles of our solute in this case. So let me write it up here, 0.0834 moles of our solute. That number is actually the bottom part that we need to calculate the molar mass. Any questions on that part there? So what's left is to actually calculate the molar mass. So the molar mass here would be the grams that was given to us, 12 grams of our solute, divided by the moles of our solute, 0.0834 moles. And that will get us 12 divided by the answer, about 100 and we'll call it 44 grams per mole would be the molar mass of our compound there in the solution. So here we could actually use, as we see, not just the freezing point to figure out where a solution will freeze, but we could use freezing point information to allow us to figure out things like the molar mass of what's dissolved in there, which in this case would be 144 grams per mole. Any questions on any of those steps there? Okay, we will lay it up there first.